Hey, welcome back to our graduate statistics course, University of Cincinnati. This is week 13 and that's our second lecture video. We are studying multiple linear regression and I've just introduced you to a problem, very simple problem, where we're trying to predict the weight of books from its volume and the type of cover it has. And I drew out for you the equation and how it's extended to add a different predictor. And I showed you the output of the model. And now we're going to work through these pieces of the multiple regression model specifically. So let's look at the estimates themselves. Again, if we take these estimates, we could write out and replace the betas by the actual values, right? So we mentioned that beta 0 would be the intercept of the model, which is of the general model, right? Which is 197.96. We can replace beta 1 by the coefficient of obtained for volume. And we can replace the beta 2 by the coefficient provided for cover paperback in particular. So because only paperback is shown up here, we're assuming that R identified hardcover as the reference level. So if you want to predict weight, just as we've done before, for hardcover books, you would plug 0 for cover, right? And this term here would disappear. So for to predict weight for hardcover books, it's like you can, because one of the variables is categorical, we can basically create a different regression equation for when books are paperback and when books are hardcover. So look, it would be a linear equation like a line when when the book is hardcover, because I'm putting 0 here. So this term will go away and the regression equation becomes simply 197.96 plus 0.72 volume, right? Now for paperback books, I'll plug 1 for cover. So this number will continue here. So we will have, let me get out of the way, we'll have the same general intercept plus 0.2 volume minus 184.05 times 1, which is just this value. So we're going to subtract this from this such that we have a different line to predict weight for paperback covers where the intercept is smaller, see, plus the same slope. All right, so we'll have 2 regression lines basically in this case, because one of the variables is categorical, right? So we basically try to fit a different line for cover, for each cover type. 1 line for paper book, 1 line for hardcover. So we're seeing that the model is telling us that we'll have different intercepts and similar slopes, these lines. So here is an illustration of that. Here is the line. So here's the equation of a line, right? So we have a line for hardcover and a line for paperback. And the line for paperback is sort of down here and the line for hardcover is up there, which, you know, kind of indicates the fact that we have that, you know, that both types of books grow in the same way with volume, which is sort of expected. But we have to add a constant that's higher for hardcover than paperback, all right? Again, the true intercept is where this line crosses the y-axis when volume is 0. Volume is never 0, so it's not interpretable, but it's basically playing the role of, you know, setting the line up or down, setting where the line should be, kind of adjusting its height. All right, so let's interpret the regression parameters one by one. I've done that in general in the previous one, but as I said, we'll go again one by one to make sure you guys understand it. So the slope of volume. Here's how we interpret it. All else held constant, meaning if I hold cover constant, then for each 1 centimeter cubed increase in volume, the model predicts the books to be heavier on average by 0.72. Now, how do I interpret the slope for cover? All else held constant, the model predicts that paperback books weigh 184.05 grams lower than hardcover books on average, right? So that's how we would interpret these two parameters here. Intercept, this one. Hardcover books with no volume, with 0 volume. And why am I saying hardcover? Because our coded paper book 1 and coded hardcover 0, and the intercept is the value of y, which is weight here, when x is 0. In this case, volume should be 0 and cover should be 0. So the intercept represents this value of the intercept. Tell us that hardcover books with no volume, which don't exist, I understand, but that's what it would say abstractly, mathematically, are expected to weigh on average 198 grams, okay, on average. But of course, there is no books with 0 volume, so it's basically telling us approximately the weight when it has only the cover in, right? Only the hardcover in. That's the closest you would get to an interpretation, but not always. The intercept is really interpretable because, you know, if we had a model with only volume, there would be an intercept because mathematically that line would cross the y-axis when x is 0, but that's an extrapolation that would never become true because volume would never go to 0. All right? So it's basically setting the height of the line. So again, the intercept really is meaningless in the context of the problem because what is a book with no volume? And it just serves to adjust the height of the line. So can we do predictions as we did before? Yes, we can. So let's practice that. Let's predict the weight of a paperback book that is 600 centimeters cubed in volume. So we have the equation here. That's the general equation. So we can simply replace things. We know that a paperback book will be coded 1. So we put 1 here. So we want to keep this coefficient in the model. And we're going to replace volume by 600 and multiply that by the coefficient for volume. And we'll keep the general intercept there. And we'll make these calculations and we can conclude that if we have a book with volume of 0.72 and we have, and we know that the book is paperback, we can expect with lots of confidence because, you know, the model is predicting about 92% of the variance in weight that, you know, the weight would be on average, that's a point estimate, 445.9, okay? Now, interaction variables. In this case, when we looked at the plot, it just feels like, and we fit the lines, we can look at these lines and see that, you know, since the first plot that we looked at, it feels like the relationship between volume and weight is the same for both books, right? We can imagine like a line of more or less the same slope being fit to these two data sets, both hardcover and paperback covers. So the model assumes that they have the same slope for the relationship between volume and weight. And it's a reasonable assumption given our exploration of the data to begin with. I remember from the very first thing we've done is to do, before we even fit the line, we look here and we see, that you can see how they move more or less together in the same direction with the same slope, but a set of points is kind of lower than the other set of points on average. And we can literally ask R to fit a line independently for each one of them to see if they look more parallel or if they look really not parallel at all, to guide us on whether or not we need to do something more than allow for a variation of intercept. And that's what we're talking about here. The way we set up this model, we set up the model in a way that we have basically two linear equations, one for hardcover and one for paperback, where the only difference is the intercept of these lines. If this isn't reasonable, if when you explore the data suggests that maybe the way they're changing, the way weight changes with volume is quite different for two levels of a different variable, it would suggest an interaction is at play. And then we can include an interaction term in the model, and we'll see that with a problem case in the lab. Okay? We'll work through that. But that's when you plot the data and you kind of ask R to fit these individual lines, and it suggests that they're not quite parallel. So it suggests to us that we shouldn't just put volume as a variable, hardcover or cover as a variable, but also volume hardcover interaction variable in the model. And I'll show you how to do that in the lab. Okay? All right, let's go to a different problem where we expand things a little bit more. I want to introduce you to this type of plot because this type of plot allows us to get an overview of a multidimensional data set, a data set that has a bunch of potential explanatory variables and one dependent or response variable. In this case, we want to know about poverty. We want to know what are predictors of poverty, right? It's a much harder thing to predict than the weight of a book, right? It's a much more complex phenomenon. So we're not going to find models with such high R-squared anymore, right? But how good can we get, right? What are good predictors of poverty? Now I want to show you something. I want to help you interpret these plots. Let's think about this particular plot here. What scatter plot is this one? So here's poverty on the y-axis, and here's a percentage of people residing in the metropolitan area. If you look at this plot, it suggests sort of a negative relationship, because the more people living in metropolitan areas, the smaller the poverty rate, right? The smaller the poverty rate. The less people living in metropolitan areas, if there's less people living in metropolitan areas, you have more poverty, right? There's a negative relationship here. And that is sort of confirmed by the fact that we can look at the R coefficient, and it shows a negative R coefficient of 0.20. And you shouldn't be surprised that it's kind of a small correlation magnitude, because when you look at the scatter plots and you imagine a line here, you can see that there is a lot of spread. If you look at the corners of the graph, you see points there, right? So there's lots of deviations. The residuals will tend to be a little large. So we can see that there is a negative relationship when one goes up, when the percentage of people living in metropolitan regions is higher, we have lower poverty. Now let's look at another one. How do I figure out what this particular scatter plot is all about? Well, I move to the variable on the left. There you go. And I also move to what's the variable in the vertical direction right there. So that has percentage of females head of households and percentage of people living in metropolitan areas, right? This looks to me like a positive relationship, also not very tight, so probably not a very large relationship, strong relationship, but a relationship nonetheless, that suggests that the more people living in metropolitan areas, the greater is the percentage of females that are heads of households. So look, let's confirm that. Yep, that's a positive and not very strong relationship either. All right. Now let's try and find something that we explored last class, the relationship between poverty and high school graduations. Take a minute and see if you can determine which scatter plot represents the relationship between poverty and percentage of high school graduates in the location. So here's percentage of high school graduates, here's poverty. So what we'll do is move up until you reach the plot that will cross with poverty. So this is it. We've seen that before, right? So that's the one. If you want to know the relationship in terms of numbers that we determined last time, first of all, let's think that this is a negative relationship, and you can see how much tighter it is compared to these two. It's a negative relationship such that the more high school graduates, the smaller the poverty rate. The less high school graduates, the greater the poverty rate, right? So if you want to get the number to indicate that, that's a negative 0.75, which is a pretty moderate to strong relationship, right? Remember, our cutoff is like above 0.8. And think about it, because poverty is such a complex phenomenon, finding a 0.75 relationship is pretty good, right? Now, why are these plots useful? For a couple of things. When you collect data to predict a particular variable of interest that you have, imagine poverty is your variable of interest, and you have hypotheses about what are the kinds of explanatory variables that could be helpful there, and you decide to collect percent of people living in metropolitan areas, percentage of white people living in the area, percent of high school graduates, percent of females that are heads of households are your hypothetical variables. You can have an overview of the bivariate relationships by looking at a plot like this, and it helps to exclude variables that are showing very weak relationships with your variable of interest. Maybe you thought it would show up as a strong or moderate. Put in context, remember, poverty is very complex phenomenon, so even correlations that seem sort of low, like 0.30, could still be pretty, it's considerable given the complexity of the phenomenon, right? It's much harder to find something like this relating to complex phenomenon. So this gives you an overview for you to start selecting variables for to put in your model. There might be also conceptual reasons to select something. For example, it may be your interest to see whether the percentage of females that are heads of households, how that relates to poverty. So if you have a state in the US that has a very high percentage of females that are the only head of the household, there's no male, there's just one breadwinner, and that breadwinner is a female. If you have a large percentage of those households, what does poverty look like, right, in that state? And we can explore this by quickly looking at how these relates here. So you can see that if you have more households where the female is the sole breadwinner, you have more poverty than on states that you have a smaller percentage of females that are heads of household, right? So you may have an interest of exploring particular relationships, but if we looked here and we found, it looks more like a circle than a cylinder, then we could okay, we stop here. But this is not the case here. You can see that there might be an interesting correlation here, and if we look at the numbers, let's look at numbers. poverty and female, a 0.5 relationship seems considerable as well. Of course, we would look at the p-values also to determine whether it's not only a 0.53, but it's also statistically reliable. But this is my long way of saying that when you have a data set, you start with an exploration of bivariate relationships. And if you're going on to model a particular response variable, you would only select variables that correlate significantly, statistically significantly, with your variable of interest. Okay? So we'll come back and select a couple of these variables and show you how they relate and build a model to show the relationships with poverty and how they show up. All right, see you soon. Bye.